our last section of chapter 10 is about solids. So section 10.5 was learning a little bit about 4 different types of crystalline solids. What does it mean when I say a solid is crystalline versus saying it's amorphous? Crystalline solids mean that the atoms or molecules are arranged in repeating definite orders. Amorphous amorphous means they're random. Okay. Many solids prefer to be crystalline. They prefer to be ordered when they come together. Okay. And your job for section 10.5 was to go through and know some of these properties for these 4 types of crystalline solids: ionic, metallic, covalent network, or just a molecular solid like sugar, CO2. Okay. And then there was a table that kind of summarized all that. All right. So to end this chapter, I want to look at a little bit of that order that's in crystalline solids. So this is called a lattice structure. The classification of a crystalline solid, what kind of order does it form? What kind of pattern does it form is called a lattice structure. Okay. So the way we determine what kind of lattice structure a solid has is using this technique called X-ray crystallography. I'm not quite sure I don't actually think I need you to know a lot of detail about this technique, but I do want you to know what it is. So when we say X-ray crystallography, I literally mean we put a crystal into an instrument that shoots, guess what, at the crystal? X-rays. Very good. Crystallography. Okay. All right. And so I want you to think about when those X-rays hit that crystal. Think about the size of X-rays, the scale of X-rays, right? It is small enough that it can actually interact with individual atoms and molecules, right? They're on the same scale. And so if it hits a crystal, if it hits an atom, what is it going to do? Boo, boo, bounce off. The word is diffract, right? Okay. We get diffraction patterns, okay? And when we get these diffraction patterns, you can do some nifty little math, right? If you have an atom here and an atom here in your crystal, and the X-ray hits and bounces off at that angle, right? As opposed to when the X-ray hits here and it bounces off at that angle, okay? We can determine mathematically the difference between that angle and that angle. And then we do some other math, and that tells us what order the atoms are in. It gives us a repeating pattern. Okay. And how do I know it's not just random? Well, if it was random, the diffraction pattern would show that it was random, right? That's how I know it's not amorphous. I know it's a crystalline solid because there are repeatable diffraction patterns. And we have determined, everybody on board? We have determined in science, in chemistry, there are actually 7 distinct crystal lattices. Sometimes we call them crystal lattice systems. Okay, there's 7 of them. Guys, this class is not where you learn all 7 of these and then all of their individual patterns within. That's not this class, okay? I'm trying to teach you that there are patterns. If none of you guys are chemistry majors, right? Everybody's like, no, not me. Unfortunately. Who's biochem, though? Anybody doing biochem? I thought you were. Damn it. Okay, fine. If you were a biochemistry major, you might have to learn about this at some point, but even then, I don't really think so. This is pretty. So, in the hierarchy of chemistry classes, actually after Gen Chem 1 and 2, if you're a chemistry major, the next class you take is an inorganic chemistry. You do an inorganic chemistry. And an inorganic chemistry is where you learn about basically any compounds that's not carbon. Because carbon compounds is organic chemistry. That's its own other class that y'all have heard about, I'm sure. Okay. There's 7, and again, I know this is fuzzy. Y'all probably can't even, again, there's 7 little systems: cubic, tetragonal, orthorhombic. You guys do not need to know any of these names, okay? What we're going to look at is the very basic system, which is a cubic system. And I'm going to teach you what this little phrase means, this phrase unit cell, okay? And that's really about all we're going to learn about crystal structures, okay? So let's see, what do I want to define first? Okay, let's do this way. Let's do this way. Let's talk about what is this word I'm using, unit cell. Let's do that first. So let me okay, so we're going to look at the cubic system. All systems have what is known as a unit cell. Crystals have unit cells. What is a unit cell? A unit cell is the simplest repeatable unit of a solid. All crystals are made up of repeating unit cell, 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 unit cell. In fact, one of the easiest ways to think about a unit cell is think of a cube. All right, 3 dimensions, there's a cube, okay? These black circles that I'm drawing right here, or that are on this picture, these represent the atom or the molecule, okay? What we call the locations of the atoms or molecules in the unit cell, these are called lattice points. This is where the atoms are located, right? Any dot is where the atom, that's called a lattice point. So they have this kind of cube-like structure, okay? And you can see on the slide how this is the repeating unit. Can you imagine taking that cube and repeating it in 3 directions over and over and over, right? See how that cube just builds up and up and up and up and up from around itself? Okay. This cubic system unit cell that we're going to talk about. I don't know that you need necessarily to know this, but I'll throw it up here anyway. What makes it be cubic in particular, as opposed to one of those other sevens that we saw that we're not learning about, but all the sides in a cubic unit cell are equal. So it really is a true cube, okay? It's not a rhombus, it's not a whatever, it's a true cube. And so what does that mean all of the angles all are? Yeah, all of those angles are right angles, 90 degrees, 90 degrees, 90 degrees, right? Okay, there are 3 types of unit cells for the cubic system. You following? This sucks, guys. I ain't gonna lie. This, when I had to learn this, well, it doesn't really suck. But when I first learned this stuff, I was like, this is Greek to me. I don't know what we're talking about. It is hard to visualize. And I don't really have the best models to show all of these cells, which is why I'm only going to talk about these 3. Because it really is something that you kind of need to see. So let's see what I can show you. So let me tell you guys first, do you see how solids like to form these very ordered crystalline structures? I gave out, y'all can look right there, y'all can look right there. Veronica, I got some right there. I set out for you guys a couple of different crystals. There's one, no, not those. Those. Yeah, those. So y'all can look around here. There's one, I think I gave you some, right? In front of you? Okay. There's one that's like this really beautiful white square. Y'all see that? Look at it. Look at how like ordered it is. Do y'all see that? Can y'all see that? That's so cool, right? Guess what compound that is? It is indeed salt. Sodium chloride. Sodium chloride is a what kind of solid? This is an ionic solid. In section 0.5, you are supposed to learn a few properties of ionic solids versus some of these other ones, right? Ionic solids. This is how the atoms of sodium chloride arrange, and they form these really beautiful crystals. This is not quite so beautiful because it didn't do a very good job of getting the crystals out when they started to form. And so some of them just kind of globbed up together. But maybe if you look at it, you can see some of the striations, like where some of it is trying to come together. This is, I think it's copper 2 sulfate. What I think this is, copper 2 sulfate. This is another ionic compound, right? An ionic solid. That big one right there, you can really see the lines, I think, better. Okay. And how are these ionic solids, how are any of these crystalline solids organized? How can we break them down to the very, very smallest thing? It's this thing called a unit cell. Okay. So when I say sodium chloride, we learned, what does that mean? How many sodiums and how many chloride ions? We know that that's a 1-to-1 ratio. If we were going to look at the unit cell for sodium chloride within a unit cell, there would have to be total 1 sodium and 1 chloride ion represented in that unit cell, because that's the smallest unit. Well, so we got to remember, so this is what we're fixing to learn. And we are actually not going to learn about the unit cell systems for compounds because it is more complicated. We're going to think about actual just like elements with just one atom. But I want you to think, look at the picture. There's for example, that atom right there, right? Let's look at that atom that's on the back corner. How many other boxes, I say boxes, you guys know I mean other unit cells, is that atom shared between? Oh, you got to think three-dimensional, guys. 3 dimensions. That one atom right there is shared between how many boxes? Nope. 8. Do you see the 8? One. Okay, here's the atom I'm looking at, right? Here's box 1. Look behind it. There's box 2. Look next to behind it. There's box 3. Look down in front of it. There's box 4. You see the boxes? Now come up. There's box 5. Remember, this atom right here is in the corner of this box up here on the top, right? There's box 6. There's box 7. Isn't that atom in this that I'm looking at right here in the center? Isn't that atom part of this box 7 back here in the back? Sure is. And there's box 8. That one atom is split in between 8. Woo, 8 different unit cells, you guys. Robert, what is going on today? Mama didn't get enough sleep. That's what's going on. I mean, technically you should be able to, but we're going to shortcut it. We're going to I mean, here's the deal. Here's the deal. Any atom that's at a lattice point at the corner of your cube, guess how many boxes it's always a part of? 8. Okay? The corner of a cube is always part of 8 total unit cells. Okay? Always. So here's how we're going to use it. Here's how we're going to use that information. So I said we're going to learn how many different unit cells that are cubic? We'll learn 3. First one actually is going to look just like this. It's called simple cubic unit cell. Okay. Simple cubic unit cell. Here's an example of an element that has this particular unit cell. I do not require you to remember that polonium is the example I'm showing you. Okay, I don't care about that. I'm just telling you that's an example. Okay, polonium. So what does a simple cubic unit cell look like? In your cube, in your unit cell cube, you have one atom at each corner, and that's it. Okay, simple cubic. One atom at each corner. Okay, so that means in one unit cell, at each corner, at each lattice point, what volume of the atom is contained in that one cube? Remember that one atom right here at the corner, yeah, is equally split between how many different unit cell boxes? 8. 1/8 of the atom is inside the unit cell at each corner. Does that make sense? You're like, not really. Let me show you this picture, and then I'll come back to this. Let me show you this picture. Okay, so here, I'm looking at this atom right here in the center. Yes? It's a sphere, right? It has a volume, right? How is that volume divvied up? Between, no, don't look at these numbers yet. How is that volume divvied up between all of the unit cells it's a part of? An 8th, an 8th, an 8th, an 8th, an 8th, an 8th, an 8th. An 8th, an 8th, an 8th, an 8th, an 8th, an 8th, an 8th. I wish I could draw that on the board, but I don't think I'm good enough to do that. Well, No, that's if you have an atom at the corner, and wherever an atom is what is called a lattice point. A lattice point is not necessarily a corner. A lattice point is where atoms are. When you have atoms at each corner, an atom in the corner is 1/8 of an atom in the corner. One-eighth of the atom is in a single unit cell corner. One of those dots is 1/8 of the total atom at that point. That unit cell has how many corners? 8. So if you have 8 corners and each corner has 1/8 of an atom, how many total atoms are represented by that one unit cell? 1, guys, yes. How many atoms in the unit cell? 8 lattice points, 8 corners, times 1/8 of an atom in each corner equals 1 atom total. Eight lattice points. Because this atom is in the corner, there's 1/8 of an atom at each lattice point. One atom total is represented by the unit cell.
So that would be the same for all of the crystal for every cubic it would be 1/8.
For every cube that we're going to look at, every cubic that we're going to look at, if something's in the corner, it's 1/8 of an atom. All the time, every time. Simple cubic. That should make sense. What is the simplest unit of an element? It's the smallest building block of matter. An atom. An element is made of 1 atom, right? Smallest repeating unit, 1 atom of an element, 1 atom. The unit cell reflects the smallest repeating unit. Yes.
So the first one is the 1 atom at each corner. The second one is 1/8 atom in corner. So the first one is
1 atom when I'm making my drawing. Okay, 1 atom at each corner. Sorry, thank you. 1 when I'm drawing, but really it's 1/8 of the volume of an atom. Thank you, Shiva. Simple cubic. Simple cubic. 1 at each corner, but really the box is inside the center of that atom and it's splitting it into 8. Okay. Next 2 types. Let's try to do these pretty quick. Oh, wait, one more thing that you need to know. So when we are talking about an atom, a whole ass atom, okay, we're talking about a whole ass atom now. How many other atoms does 1 atom touch? Now look at this picture and look at these numbers. Let's think about 1 whole atom. And how many other atoms does it have direct contact with? 6. Y'all see that? No matter which atom I was talking about, let's say I was looking at this one, it would still be in contact with 1, 2, 3, 4, 5, 6. See? In a simple cubic unit cell, this is what we call the coordination number. The reason I'm teaching you this is because it's an easy test question for me to give you. If we were doing crystallography, this coordination number has some impact. It means something. For this class, for now, I'm wanting you to get the idea that this is three-dimensional in your head. And if it's three-dimensional, then that atom has direct contact with how many other atoms? 1, 2, 3, 4, 5, 6. Okay. Direct contact. All right. Next type, body-centered cubic unit cell. So simple cubic unit cell, okay. Body-centered cubic unit cell. Sometimes this is referred to by the initials BCC. BCC, body-centered cubic. I don't know if you want to write that down. BCC. At a body-centered system, body-centered cell, unit cell, you still have, quote unquote, right, Shiva, now, quote unquote, one atom at each corner. But then there's a whole ass atom right in the center of the unit cell. You see that in this picture? Yeah. Okay, you guys see this? You still have atoms at the corner, at each 8 corners. You can't really see the one that's supposed to be back here in the back, but it's there, okay? But then you have one additional atom right in the center of the unit cell. And so, how many total atoms does a body-centered cubic unit cell contain? Yep. Why would it do this as opposed to the simple? Is that what you're asking? Because it's bigger? So elements that do this type of units, that have this type of crystalline pattern, typically like this pattern because of types of intermolecular forces that are going on. They like to be packed together more tightly than elements that do just the simple. And sometimes that's a size restriction. Smaller atoms are more likely to be able to do this type of cell as opposed to big fat atoms that can only get in the 8 corners and that's it. Okay. Here's body-centered cubic. I've got a, God bless you. I've got a little model of it. Y'all can pass it around if you want to. See how there's one in the center? Yeah. Okay. Did that? Okay. It's 2 total because there's an 1/8 of an atom at each of the 8 corners. So 8 times an 8 gives you 1 total from that. And then another whole ass one right in the center. That's 2 total. Okay, coordination number for this type of cell is 8. So for coordination number, I'm just going to write capital C, capital N. Okay. Coordination number. How many other? Sorry, one more time. Sorry. What'd you say? Other atoms. Other atoms. A atom, a single atom, has direct coordination with 8 other. And the easiest way to visualize that is think about the atom in the center. How many other atoms does that atom in the center have direct contact with? The other 8 in those corners. 1, 2, 3, 4, 5, 6, 7, 8, right? Okay. Guys, really, I'm telling you, just memorize this stuff, okay? Just memorize it. Easy multiple choice question, right? Just memorize this. Okay, last type. Face-centered. Face-centered. If you have a face-centered, actually, I'm going to come over here. If you have a face-centered unit cell, you have still atoms at each corner. So there's 8 lattice points now at the corners, right? Every time you have an atom somewhere, that's a lattice point. There's 8 because there's one at each corner. And then face-centered means there's also an atom on each face of the cube. So look at this image. See how, let's look at, if we were looking at this face of our cube, see how that red atom is cut right in half? Because at the face, an atom is split between how many unit cells? 1 unit cell and then another unit cell, 2 unit cells. So atoms at the face have how much of their volume in each? Half, exactly. Okay. Sometimes this is called FCC for short. I don't know if that abbreviation comes up in the active chem question or not. I'll probably just use the whole phrase. But if you see FCC, that's what this is. Okay. Here is a model of an FCC unit cell. I'm going to pass it around. See if you can observe the 8 atoms at the corners, and then how many atoms on how many faces? How many faces in a cube? How many faces are there? Like a die, right? 6 sides. Okay. So if I've got, no, don't start that way. Start this way. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. 8 atoms at the corners. So that's 8 corners, 8 lattice points, times an 1/8 of an atom's volume, plus, now we'll see how good I am in 3 dimensions. I'm not. Let's try. Okay, face on the top. Face on this side. There's an atom. Face on the bottom. Face on this side. Face on the front side. No, don't like that. Don't like that. Don't like that. Face on the front side. Face on the back side. When you look at the faces, how many face lattice points are there? 1, 2, 3, 4, 5, 6. And like we just said, how much of an atom is at each face? Half. And so how many total atoms are in a face-centered cubic cell system, unit cell? 4 atoms total are represented by this type of unit cell. And then the one that's hard to figure out, and so we're just going to go, I mean, it's hard to visualize. Okay, what's the coordination number? It's 12. Just say, okay. Okay, Ms. Poe, it's 12. Okay, it's 12. Commit to memory. It's 12. It's coordination number 12. Okay. An atom, I know, right? It's kind of hard to, I need a better model to show that it really is 12. I know, you can sit here and be like, it gets kind of, okay. All right, guys. That's it. I decided I'm not going to talk about ionic compounds. We just looked at for elements. That's it. Okay. We're not going to talk about ionic compounds. We just looked at elements. Okay. Know those three. And that's the end of chapter 10. Okay. So, reminders. Ooh, and an announcement that y'all are either going to hate. Well, no, you're going to hate it. It's fine. But it's for your own good. So, all right. First thing, second homework set for chapter 10 is due Saturday night. I have decided that I want you guys to go ahead and take a quiz in Active Chem over just chapter 10, rather than waiting until next week to do a quiz over 10 and 11 before the test on Thursday. I'm gonna split it. Yeah. Mm-hmm. So, okay. In Active Chem, you'll go to the quiz tab, and this chapter 10 quiz will be there. It has 10 questions. Active Chem's suggested time was 30 minutes. You and I know that Active Chem overestimates your abilities. Just be real honest. So I gave you guys an hour and 15 minutes. Okay. I want you to be thinking about this is timed, like your exam is timed. Okay. You need to try to work these problems under a time constraint. I don't think 30 minutes is a fair time constraint. I do think an hour and 15 minutes to work 10 questions is a very fair time constraint. Very fair. Especially if one of the questions is, what's the coordination number of an FCC unit cell? If you take 5 minutes to answer that question, I swear to God. Okay? Okay?
Is it like one question is presented at a single time, or is it like a whole? Does not that matter?
It is presented one question at a time. You can get, I give, on my quizzes, I give 2 attempts per question.
So it tells you if you're right or wrong?
Tells you if you're right or wrong, gives you the feedback on the first attempt. You can try again. Doesn't take off. But you do only get, now can you go back? Anybody remember from last semester? You can skip a question to go to another one and then go back to one thing. But once you do your 2 attempts at that question, then that's it, right? You're done. Yeah. Okay. What else? Guys, from last semester, anybody, what about quizzes? I mean, obviously remember to do them, right, John?
Are they like, what is it, are you ready or is Active ready for sync stuff?
It's all Active Chem graded.
Obviously I'm trying to correct sync things, but
obviously, but yeah, no, it's all Active Chem. When do you have to do it by? Monday morning. The last time you can start the quiz would be 10 o'clock Monday morning. And that would give you time to do it at 10, finish by 11:15, and get your butt here for class at 11:30. But do it before then. Do it whenever you're ready. You don't have to wait till Monday morning to do it. Do it whenever you're ready. Like Sunday, Saturday night, whatever. Okay. I'm going to stop recording. Let's go ahead and take our little break, and we'll get stuff pulled up for chapter 11. Yes? Deal.
So it's already open.
I